talk from Dan Popa from University of Texas, Arlington, on running human-like facial expressions for the Android Phillip K-Dick, which is also one of David's robots. So let's first have a round of applause for David. Continue to hear a bit more about what you can do with learning for Phil Dick.
All right. Well, thank you. So it's great to be here, and also my talk basically will take from where David left off and show you a little bit behind the hood on what's going on with the puppeteering. But actually, what my talk will be going towards is what happens if we take that Kinect and we present it to Phillip K. Dick, so that now Phillip K. Dick's expressions could be sensed and in turn used by him to change his behavior on the fly. Okay, so imagine that now we're taking the Kinect and presenting the robot to the Kinect.
I'm sorry, is this from a database or is this from a puppeteering point of view?
This is going to be related to online learning, but
okay.
I'll get to that in a second. So my lab at UT Arlington, we do three basic things, but they're mostly related to control and learning for human-robot interactions. So one of the projects currently going on is creating robot skin, which is sensorized to do physical human-robot interaction. So imagine a whole arm is covered with this material. You can essentially guide it, kinesthetically teach it, or provide safe behavior. And this would be used in industrial robots as well as humanoid robots. Another topic which I'm going to talk today is interacting with the robot using by recognizing different poses and gestures and then synthesizing them. So we've done quite a bit of work with Zeno, looking at simple behaviors like face tracking and motion control of the neck and eye motion together so that the interaction appears realistic. So here you see a problem with saliency. A robot was tracking one person, there's another person that And another topic here is, let's see if I can play this video. Interaction with robots using non-intuitive interfaces. So in that case, there's a headband controlling this mobile manipulator. So the question is, how do you map the input space, that is the gesture input from a person, to the actions of the robot? So in this case, he blinks his left eye, the robot takes the left.
Sure, right here looks false, and that robot is very well.
Yes. But you see the problem. It's sort of an arbitrary mapping. So the question of adaptation would be: you start with some guess of this mapping, but then you want to change that to help the human operate the robot in the way. So coming back to this problem of uncanny valley, there are four very important components of HRI. Right? On one hand, there's appearance, and so here David's robots are unprecedented in terms of what they can offer. And so if you make the appearance unlikable, then that's the first step, right? And you have to fight against that. So you have to tune the appearance to be likable to begin with. Then there is dialogue in the sense of speech, right? So we talk and then we expect a response. If that is not tuned and realistic, then we are in the valley. So if the robot starts with a shrieking voice that is not tuned to the appearance, then there's a problem. Facial expressions. If facial expressions start to be unpleasant for us, right? If the expressions are totally disgusting, then we're going to be in the valley again. And lastly, body language. So if you have a body or if you have a neck, then you have to tune those expressions as well. So I think that this problem of uncanny valley is you have to work on all those four things. And if one of them is off, then you're going to be in the valley. But if you can tweak all of them at the same time, I think we're not going to have a problem with the uncanny phenomenon. So I met David in 2005, and of course, you know, he's already shown you this work with Einstein. So since then, we've also worked with Zeno, so we're looking at imitation. So this is monkey see, monkey do. So we're looking at imitation studies with children, in particular autistic children, to see if we can actually quantify autism severity from motor markers. So the idea is you have a robot present a certain social action, such as waving, or another social cue, fist bumping. Then you see the response, and you can on the fly compare the motions. And if the motions are very dissimilar, you can say, well, this person doesn't have social skills, or this person is more autistic. So we try to test that hypothesis. And so I'll show you this video. We have Zeno perform certain actions. These are scripted actions in this case, where we can have a puppeteer in the background do those actions, and then we see what the child does. So this is actually my son in a motion capture lab, trying to keep up with Zeno. This is a video which I recorded he was 3. And so you can see that he imitates the motion. Now, we're not looking at exact, but sometimes he doesn't. We're not looking at exact temporal match, right? But we're looking to see that the motions are similar. Okay, so then we can look at how well these motions are imitated. So in the going back to this idea of adaptation, so we use reinforcement learning, sort of a different brand of reinforcement learning, which works online. A big fan on online schemes. This first appeared and was called animal learning, and this is how we learn. But these learning schemes happen continuously. This is not batch processing. You present a whole bunch of data, you learn it, and then you play it back. This is more like adaptive control. So I was actually very happy with Mark's talk this morning, because this is the key to learning behaviors, optimizing behaviors. You just have to provide these connections and the tools, and then turn this on if you have different neural nets or different neurons, right?
And it converges. I mean,
You turn it on and it just works. It's like magic.
It's so wonderful.
So the key is how you connect it. So in the case of the interface, here's how we've looked at it. So this is a scheme called TD Lambda Temporal Difference Learning. It's been around for about 20 years. And you have a policy, an actor. Typically this is the robot, right? You have a certain control policy which changes by a critic. So you have a critic that's evaluating whether the behavior is positive, the cost function is minimized, and you have a bunch of rewards. So typically, the learning has occurred in the past through this policy. So what we're doing lately is actually we're not learning any policy. So when you're teleoperating, what is changing is actually this map between the interface input of the operator and the effect it has on the robot. Okay, so it's slightly modified. What we're saying is, imagine you have a joystick and you're driving a robot, right? Somebody has set the gains on that joystick, right? Your action, let's say with one of the controls leads to some velocity and some degree of freedom, right? But that is preset. What we're saying is that based on the results, we want to change that mapping on the fly using this DD line. Okay, so that's very powerful, because essentially we are helping the user control the robot better online. So another application of this is this problem of head-eye interaction. So the problem here is with a humanoid robot exhibiting a property of joint attention. You want a robot to recognize a human and track the human. So the question now is, how do we do it with joint motion of our neck and eyes, right, so that it appears realistic? It depends on where the object is, how fast it moves. So if it's close to my eyes, then I want to move my eyes to track it. And if it's far away, I want to move my head. And if it's in between, I want to have a combination of the motions. So we have, on the one hand, a user that's tracking an object on the screen, so we can actually record the combination of neck and eye at the same time. And then we compare that with what the robot does. In fact, we can learn that and then play it back to the robot, and the conversation will appear more natural. So we have recently, I've been hosting Phillip K. Dick in my lab, as well as so the same basic demo that you see here is running with the robot through a simple Kinect. Search operator for selecting the expressions. This is essentially automated, so you take your next generation Android, you present it to the Kinect, it runs through this data collection, and then at the end of it you have tuned expressions. So it's general enough to be used on human-made Androids or non-human Androids. So in the future, we want to look at design improvements on the robot itself that will actually minimize this difference. And another thing I wanted to say is, in this case, face and eyes, and so some of the accurate space of the robot is decoupled. So mouth motion has a little to do with eyebrow motion. So it makes no sense to train neural net for the whole space, so we have it decoupled right now. But we want to actually look at full face, not just mouth, but also eyes and so on. Also couple that with neck and eye movement. So the goal would be to try to lip sync. So you can recognize speech as well as expressions and generate them in a natural way for the robot. So I want to acknowledge 2 grants from NSF supporting this work, and some help from Hanson Robotics and indicators such as this. Thank you very much.
All right. Well, thanks for the talk. And any questions for Dan?
Sure. For future work, the extension into non-ectomic classification of facial expression would require mapping between the full range of possible expressivity of the face and a context, like the social context, for example. So, a professor of mine at UT Dallas, Alice O'Toole, about 10 years ago, was capturing natural expressions elicited by Disney movies. So you had test participants that would sit alone in a room. There was nobody watching them. There was a camera watching them, of course, but they were watching a Disney movie, and they would spontaneously emote as the movie was played, and the expressions never repeated. You could sometimes classify them, but often the expressions and their variations were awkward to fit into the facial action coding system for measurement, and always different. And what the differences were certainly weren't classifiable by the new facial action coding system. What the meaning of those differences remains a mystery, effectively. The ability for robots to generate those facial expressions can kind of pop out of a system like this naturally, but what they mean and how you play them in a context and recognize them in a context, it seems like a rich area for investigation. do you have any ideas or plans for how this might be used for exploring that?
So I would say to that is I go back to this animal learning. So don't worry about this here, but just this. So key here is that if you have the right rewards and if you have the right critic, this will always work. But the key is what is the right reward, what's the right critic. So who's the critic? So I would ask you, who's the critic of whether those expressions mean something or they don't. So if you have a way to evaluate them, I mean that would be one. And then you would want to encourage some and discourage others. So if you can tell PKD how to do that, then he can select those, he can arrive at those emotes that may be more playful or spontaneous or more human. But the key is how to evaluate them and how to describe them to PKD.
So if you were collecting data from human interactions, enough data about the context and the expressions elicited. So for example, in that Disney movie, you could be recording the Disney movie using some kind of intelligent system to try to understand the semantics of the content in the Disney movie, the emotional meaning to the human mind, right? And then understand basically classify the various expressions that humans would spontaneously affect while watching the movie, and then you would have some kind of semantic classification of expressions in a social context, which doesn't necessarily give you the reward here, but if you can say that then those expressions serve some purpose in a social context.
That would be the critic.
Right, exactly. So if we were making expressions at each other, we are, as we're talking right at this moment, unconsciously, we can't help it, right? It sort of flows out of us. What was the evolutionary reward for making these kinds of expressions in that context? And so we have the behavior, we could have the behavioral information in that social context, but figuring out the human reward structure could then give you the reward, perhaps to make it super normal, maybe hyper manipulative, if you had, or effective affect in a social context.
So again, I don't have the answer to your question, but I know that if we can work on the reward and the critic and put the right inputs there, you can get some very nice behavior, which may be easy to implement too.
Yeah, it seems that when humans learn to make appropriate facial expressions, we're relying on quite subtle cues in the facial expression of the other person. So it's not like we're just getting a high-level reward signal, like this facial expression is good, or this facial expression I'm making is bad, and then we have to do such a complicated assignment of credit now to figure out like how much credit this little actuator movement in the jaw gave, or this little actuator movement in the side of the eye gave, to get this good or bad signal. So now we recognize something subtle in the other person's face, which through some kind of combination of inbuilt and learned wiring, we can then map to corrections to specific parts of the face. Like I think at some level, if I make a face that looks wrong and you react somehow, I could trace that back to what's happening in my mouth, or maybe the way I was looking in my eye, without having to do so much search as a reinforcement learning algorithm would have to do the assignment of credit. So there's some subtle perception, action, feedback there that helps with reinforcement learning.
You've been presented with lots of faces, and of course you started by imitating others on some level. But with humans, we have the same anatomy, so the face that you make, you know, I can make the same face with the same muscle.
Are you sure? Can you do this one?
Yeah. but PKD doesn't have the same muscle, so it's a little more difficult for him.
But it would be interesting to see what would happen if you're in the critic. You took not just the profile of the actual motors that are used, but also the limit stops. So when you set a servo, right,
Yes.
there's a maximum minimum limit. Say, for example, you're watching